we should, huh? Let's see. Don't tell me. It's coming. Hold on now. Shoot, tell me your last name. Aha, Tanner. Yes. Can you check the lights forward? The one on the so closes the door. Yep, that's the one. So, theorems involving zeros of polynomials. There's two theorems we're talking about today: rational zero theorem and conjugate zeros theorem. That second one there takes like 40 seconds to talk about. The conjugate zeros theorem is really easy, real quick. The first one takes about 40 minutes. There's a lot to it. Rational zeros theorem. Does anybody happen to know what the word rational means? I know that's a tough question to ask teenagers because rational teenagers is kind of an oxymoron there, but rational, anybody want to take a stab? As it pertains to mathematics, what is the word rational? What are rational numbers? Maybe let me ask that. Rational numbers? You guys should know this. Okay. Ooh, you're close. Pi is irrational. Yeah, that's a good part of it. Yeah, that's a big part of it. What do you think the root word is of the word rational? Ration? Kind of. What's the root word of ration? Ratio. What is a ratio? Something compared to something else. A ratio is a fraction, you guys. The root word here is fraction. Rational numbers, then, are numbers that can be written as fractions or ratios. So, and it's more than what you think. All right, you're probably all thinking of just plain fractions now, right? But is 5 a rational number? Could 5 be written as a fraction? 5 over 1. 5's a rational number. What about negative 10? Is that a rational number? Could negative 10 be written as a fraction? Negative 10 over 1, is that a fraction? So that's a rational number. There's a lot of rational numbers. What about decimals? Can decimals be written as fractions? What about 0.5? That's just 1/2, right? So some decimals are also rational. The point I'm trying to make is there are a lot of rational numbers. Is every single number out there rational? Can anybody think of one that's not rational? You can put any whole number over 1 and make it a fraction. Yeah, you're right. What about pi? Pi is not rational. Root 3 is not rational. Root 2 is not rational. Root 7 is not rational. There's a lot of irrational numbers. Any prime number that you square root, would be irrational. Anyway, there's a whole bunch of different types of numbers. There's rational, irrational, imaginary. We're talking about theorems involving rational zeros. Anyway, I want you to write this. What's that red doing there? Hold on now. Write this polynomial down. X to the third minus 10x squared. Plus, this is really hard to write with a mouse. Plus 6x plus 20. Write that down. Come on, what are you waiting for? Go, right.
Consider that polynomial. I've had you label a few things. This one at the end is called a constant. That's going to be important here in about 5 minutes. Now you've seen that I've drawn a line here to this number 1, and I haven't showed you yet what I've labeled that as. I want to see if you guys are clever enough to come up with it. What's a number called in front of a variable? Coefficient. So that is a coefficient. It's right at the very front of a polynomial. So it has a special name. It's called the leading coefficient. I want you to label that number 1 as the leading coefficient. There's a leading coefficient, there's a constant. That's important. What we're going to try to do for this polynomial is find the zeros.
We're trying to find the zeros. If this were a test question that we had just barely done,
how would you have attempted to find the zeros? Let's talk about that. Factor by grouping. There aren't any common terms. So
if this were one of your test questions, you would have tried to factor by grouping. Let's see what that would have looked like. Thank you. But we would have run into a big problem. If we would have tried to group here, and then tried to group here and here, what would have happened? From the first grouping, we could have factored out an x squared, and that would have left us with x plus 10. But what comes out of that second group? What's the common factor between 6 and 20? One's a common factor, but what's the greatest common factor? 2, right? 2 divides into 6 and 20. Ooh, you guys are making me worried. I asked you the greatest common factor of 6 and 20. You're like, That's like a 5th grade math problem, you guys. What's the biggest number that divides 6 and 20? 2. We okay in there? Or you're not gonna have a freak out session here, are you? You take out a 2 from each of those, and you're left with 3x plus 10. Do you see the problem that I'm saying? This is a big problem. These don't match. The x minus 10, the 3x plus 10. That means it doesn't factor by grouping. That means it doesn't factor at all. Well, what the crap? If the quadratic formula only works with x squares, unfortunately. So we can't find the zeros using the techniques that we know about. We have to find the zeros another way. And this is the other way. It's called the rational zeros theorem. You use this when factoring by grouping doesn't work. Okay? Did we have to use this before? No. How come? Because the ones I gave you factored by grouping. I gave you ones that would factor by grouping. Not every polynomial like this factors by grouping. Actually, most of them don't. So write the theorem down. And then we'll talk about it. I know it's like, oh, that doesn't even make sense. Write it down anyway, and then we'll talk about it. Let's make it make sense, because you guys are smart. We can make sense of this. We can talk mathematically and still have a coherent conversation here. If a polynomial, we okay on what a polynomial is, right?
Yeah.
Okay. If a polynomial has integer coefficients, right? Integer is just a number, like 2 or negative 10. A whole number really is what an integer is. So if a polynomial has integer coefficients, does this polynomial here have integer coefficients? Yes, it does. All of the coefficients are just whole numbers. There's no decimals or weird fractions. Then any rational zero is of the form p divided by q, where p are the factors of, that's a q, yeah. What does it look like? No, it doesn't. That's so obviously a Q. Did anybody think it was a Q? Be honest. 1, 2 people. That's a Q. Any rational zero is of the form p divided by q, where p are the factors of the constant, and q, that's so obviously a Q right here, Q are factors of the leading coefficient. So, you also need to write this down as well, because students often misinterpret this theorem. This theorem only gives a list of possible rational zeros. This theorem doesn't tell you what the rational zeros are. It gives you a list of what they might be. This theorem gives a list of possible rational zeros. So let's make sense of this P and Q nonsense. We are okay that this is a Q now, huh? Okay. So P are factors of the constant. With this polynomial that we are working with, the constant is 20. Yes? So then P would be a list of all the factors of 20. Factor means numbers that divide evenly. So start yelling them out. What are numbers that divide into 20? 2, 1, 4, 5, 10, and there's one more. It's not 0. We don't want to divide by 0. 20. And 1. That's only half of them, you guys. We're missing the negatives. There we go. All of those negatives. So write these down. These are all the factors. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, 10, and 20. Those are all the numbers that divide 20 evenly. Would you agree? Okay, I'm glad we all agree. Now we got super lucky here for Q. Q are factors of the leading coefficient. But what is the leading coefficient? 1. What are the factors of 1? All right, let's write them down. Well, no, not all. That's not all the factors. There we go. Plus or minus 1. Write that down for Q. Q equals plus or minus 1. We okay so far? Where did P come from? Where did all these numbers come from? Factors of the constant. Where did Q come from? Factors of the leading coefficient. Now what the theorem says is we have to form a bunch of P divided by Q numbers. So what we have to do is take all these factors of P separately and divide them by all the factors of Q. So the nice thing about this is, what's Q? Plus or minus 1. If you divide something by plus or minus 1, does it change what you were dividing? No. You understand? True. I mean, it changes the sign. So if we took all the factors of P and divided it by plus or minus 1, then our P divided by Q list is essentially just going to be the numbers from P. But we need to state this. This is P divided by Q. P divided by Q would be plus or minus 1, plus or minus 2, plus or minus 4, 5, 10, and 20. Yeah. Yeah. And wake those guys up out there. Make sure they're not sleeping. So here's what I mean by some students misinterpret this theorem. They would look at that list and say, all right, those are all the zeros of P. Those are all the zeros of the polynomial. That's way off. Okay? Because what was the kind of polynomial we were dealing with, a third degree? Right? How many zeros can there be? 3 only. This is a list of possibilities. We've got to go through and find out which ones are or are not zeros. How is that to be done? Do you guys recall a test question on the back side of the test where I asked you, is this a factor of that? Do you remember that question? Yeah. How did you prove to me that it was or was not? Using synthetic division, but what was the actual proof that it was or wasn't? The remainder had to be 0. Well, what do we get from factors? Why are factors so important? What do we get from factors? Zeros come from factors. You guys following? So the way that we show that these numbers are or are not actual zeros of the original polynomial is we have to do synthetic division and find which ones get remainders of zeros, which ones do not get remainders of zeros. It's not as bad as you think. It really is. And trust me, I'm a math teacher. Let's try it though, and let's try plus 1 first, and then let's try negative 1. Let's see if any of those have remainders of zeros. Is 1 a 0? We got to test it.
So set up the synthetic division problem. You can do this. You should be able to do this. We just finished taking a test on it. Is the number 1 a 0 of the polynomial? And again, just so we're clear, or that I'm clear that you're clear, how do we know if it's a 0? If the remainder comes out to be 0, exactly. So let's just flow through this. It shouldn't take long. Drop down to 1. Now what? 1 times 1 is 1. Now what? You add to negative 9. 1 times negative 9. Negative 9. Now what? Add to negative 3. 1 times negative 3 is negative 3. Uh-oh. What does that show? That it's not a 0. So it was in the list of possibilities. It didn't turn out to be 1. Cross out the 1. It doesn't work. What about negative 1? Oh, negative 1. That's got to work, right? It's such a nice number. It's got to work. Does it work? Let's see. Drop down the 1. 1 times negative 1 is negative 1. There we get a negative 11. Multiply and you get a positive 11. If you add those, you get 17. Here you get a negative 17. And dang it. That did not work either. 1 and negative 1 didn't work. Shoot. What's the next one we ought to try? Hey, 2. Positive 2? Can we try positive 2? We're not having much luck, though, are we? You guys try it. Don't watch me. You do it. Does 2 turn out to be a 0 of the polynomial? I sure hope it does. I'm getting tired of all this synthetic division. Maybe. Does it work? It does? Are you sure? Well, I don't know. I don't trust you guys. I got to try this here. All right, we get a 2. We get a negative 8. 2 times negative 8 is negative 16. Oh, my word. Look at that. Hey, we found it. There's the answer. Is that all the answers? How many zeros are there supposed to be? 3. Dang it. We found 1. You can see how this might be sort of a long process, right? Yeah. So, here's the thing. Let's refer back to the discussion we were having before. Is every single number in the entire planet rational? No. This list only contains a list of the possible rational zeros. Now you got to think really hard here to a couple of days ago. You remember the worksheet I gave you where we had to solve polynomial equations, and sometimes we got weird answers like 2 plus 3i or 5 plus the square root of 3. Remember those? From the quadratic formula. Are those rational numbers? No. So what I'm getting at, we found one zero that is rational. Does that mean all of the zeros have to be rational? You understand what I'm asking? Let's refer back again to where all of the answers we got on that worksheet, I think it was 1.4 worksheet, were all of those solutions rational solutions? Some of them were irrational, right? Or some of them were imaginary. Those type of answers wouldn't be in this list. Okay? It's really important that you guys have your brains turned on right now to try to understand this. Are all of the solutions to this polynomial equation contained in this list? They might be, but do they have to be? No. What kind of solutions are contained in this list? Rational. Only the rational ones. Okay? Not every solution is rational. The reason I'm bringing that up, we could go through all of the other numbers and not find any more zeros. What does that mean? Does that mean there's only one solution? What does that mean? The other two are either irrational or imaginary. So I'm not going to expect you to go through all of the numbers and test every single one of them. That would be stupid. That would take way too much time.
Okay? Here's what we're going to do. Turn your calculators on.
Do you remember what another name for zeros? X-intercepts, right? What if we just graphed the polynomial and took a look at the graph and saw where it crossed the x-axis? Wouldn't that tell us about the same thing as what we're doing here?
Let's try it. Let's see if it does. Go to your graphing calculator, type in the equation. We got x to the third plus something something. What is it, minus 10x squared plus 6x plus 20. Now I'm gonna. I've messed up my window pretty bad, so I gotta fix it. Let's do negative 23.5. 23.5. I'm gonna do negative 10 and positive 10 for my y min, y max. Change the scale to 1. Boom! There we go.
So, how many x-intercepts do you see? Quick, come on, quick. 3. You got to think for just a second before you answer them. Do all 3 of those x-intercepts have to be rational? They don't have to be.
Alright, they don't have to be. Now, my calculator screens here are pretty small. Yours is even smaller. It's kind of hard just to glance at that and see exactly what the x-intercepts are. So I'm going to show you just a couple of tricks here. Everybody hit the zoom button for me real quick. Hit the zoom button. Come on, do it.
There's a lot of options here. One in particular that I like to use is called ZBox. It stands for Zoom Box. I want you to hit enter on Zoom Box. You see that little blinking cursor right on the origin? I want you to move that up and over to about, I don't know, right about there. That's good. Break on, okay? Now hit enter. It turns it into, instead of a little plus sign, it's a box now. Drag that box down over the x-axis and now drag it across all the way until it covers all 3 of those x-intercepts. You know what this function is called? Zoom box. Once I hit enter, the graph is going to zoom in on this box I've created. Why did I put the box right there? That's where all the zeros are. I want to zoom in on all the zeros and see what they actually are. So hit enter. Now, unfortunately, you can't just trust the calculator. Okay? Here's what I mean. You see where my finger is pointing right there? What number does that look like? It looks like -1, doesn't it? But we already tested -1. Did -1 actually turn out to be a 0? No. So is the calculator wrong? It's not. It's just that that 0 is really, really, really close to -1. It's like -0.99, but it's not -1. And here's what I would suggest that you do. And rather than just looking and say, hey, look, -1 works. Hit trace. Everybody hit trace. Do it. Hit trace. And then type in the number -1 and hit enter. What's the point at -1? -1 comma 3. -1 isn't an x-intercept because y doesn't equal 0. Okay? So that one's gone. This one is not an x-intercept. This is the y-axis right here, so that's not an x-intercept. What does that number look like right there where my finger's pointing? Looks like 2, right? Now we already tested 2, but let's just make sure. Type in the number 2, hit enter. Is 2 actually an x-intercept? How do we know? Because y equals 0. What does this one look like? Kind of looks like 9, doesn't it? But do we even need to consider 9? Was 9 on our list at all? No. Not even on our list, and if you're wondering, well, type in 9. 9 is not even an x-intercept. So here's what I'm getting at. You guys listening carefully? You have to give me this list, P divided by Q. You've got to show me that on your assignment and on your test. Okay? The next thing you do is go to your calculator screen and just start looking. All right, it looks like 2 might work. It looks like this one might work. Find ones that you think work and test those. You don't have to go through all of them. Okay? You guys understand me? Once you find one that you think works, prove that it works. It looks like 2 worked, right? Now you would go back and actually show me this and prove that it works by showing me that it has a remainder of 0. So you don't have to test all of them. Go to your graphic calculator, see which ones actually do work, and then show me that they work by doing the synthetic division. So you understand what I'm talking about? Well, these ones, you're talking about all three on the graph? Yeah. We already knew those wouldn't work because we typed in a number like -1, -1. You don't have to show me those. Just show me the ones that you know will work. You guys understand it? Let's do a quick example other than the one we just did. So, this was that problem on your test I had to cross off because it wouldn't have worked
Using factoring by grouping.
but now we know how to work with it. So write it down. This is another example. Use the theorem to find possible rational zeros. And use a graphing calculator to show which ones actually work. So maybe we still ought to work together on this if you're a little
fuzzy on what to do. What are the factors of P? Where do we get the factors of P from? What number in this polynomial? The 27 at the end. So what are the factors that multiply to 27? 9, 3, 1, and 27, right? Those are all the factors.
and their minuses. So plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27.
And we got lucky again, dang it, the leading coefficient. What's the leading coefficient? 1. That's so nice when it's 1. Because the factors of Q would just be plus or minus 1. Wait, is that a Q or is that an 8? What is that? It's a Q! My word. So then the P divided by Q list, if Q is just plus or minus 1, then P divided by Q is always just going to be your P list.
Thank you. A question for you. Don't tell her anything. Does that look like an 8 or a Q? See?
That one was kind of cute. That was like a challenge.
Which one? The first one?
Yeah.
Where was it? Right here?
That was like an 8.
Does that look like a Q or an 8? You guys are liars. Anyway, back to this. Thank you.
So,
Just so we're clear, that I know you're clear, is this all of the zeros are here? All of these are zeros, yes? Those are possibilities. Those are possibilities. Which one actually are zeros? How do we know?
well, to know for sure, we would do synthetic division, right?
But rather than having to test all of them to know which ones, the shortcut would be the graph.
I'm recording this, by the way. You guys are just coming in, so pop some popcorn tonight and watch the video. Put on the surround sound, big screen, you know, all the good stuff. So if we go to the graphing calculator and type in the equation x to the third times, minus 9x squared plus 27x minus 27. Ooh, I hope we get lucky here. Do we find one?
It looks like 3, or kind of like 3, right? We can't just go off how it looks. Hit the trace button, and then type in the number 3. So does 3 actually work? Yeah, it's 3, 0. So that does prove, I mean, this would be a proof that it's a 0, but I still want you to go the extra step and use the synthetic division, okay? Even though we already know that 3 works.
There is no question that 3 works. Do the synthetic division. Show me that it works.
So when you do the synthetic division here, this is what you ought to get.
All right, let's do problem number 6 off the worksheet. So you can put this on your worksheet. You don't have to put this in your notes. Just write on your worksheet. The directions clearly say.
State the possible rational zeros of each function. That comes from the P over Q list. And then it says state which ones actually are zeros. Find all the rational zeros. So, what's the list for P?
The factors come from the -6. What are the factors of 6? 1, 2, 3, 6. Plus all plus and minus. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. The difference here is that Q comes from the factors of the leading coefficient. Now we have a leading coefficient of 2. Dang it, what are the factors of 2? 2 and 1. So this changes how we form the P over Q list. I mean, not how it formed, but
There's more P over Q. So the way that this works, it's really not that hard. Just start with one number of p and divide it by each of the factors of q separately. What's 1 divided by 1? So then your p over q would start with a 1, plus or minus 1. We're still staying with the plus or minus 1 here for p. What's plus or minus 1 divided by plus or minus 2 now?
Plus or minus 1 divided by plus or minus 2. It's 1/2, right? Plus or minus 1/2. So you have a plus or minus 1 and a plus or minus 1/2 on your list. Just use fractions, no decimals. Now move over to the next number for p. So starting with plus or minus 2, now divide that by each of the factors of q. What's plus or minus 2 divided by plus or minus 1? Plus or minus 2, right? Now what's plus or minus 2 divided by plus or minus 2? 1. And don't we already have that on the list? So we're good there. Now move over to the 3. Plus or minus 3 divided by plus or minus 1 is plus or minus 3. Plus or minus 3 divided by plus or minus 2. It's,
Just leave it as the fraction. What's plus or minus 3 divided by plus or minus 2? Plus or minus 3/2. Just leave it. It is 1.5, but just leave it as a fraction.
okay, now go over to the 6. What's plus or minus 6 divided by plus or minus 1? Plus or minus 6. And then plus or minus 6 divided by plus or minus 2? Plus or minus 3, but we already had that earlier, right? So those are all of the factors of p over q. 1, 2, 3, 6, 1/2, and 3/2.
Okay. So that's one part of what you have to show on your worksheet is this list right here, the p over q.
You have to find the rational.
Now we have to find which one of those work.
Are all of those rational? What does the word rational mean? Can be written as a fraction. Couldn't all of those be written as fractions? So those are all rational. Each one of these is a potential rational zero.
We got to find out which ones work. How do we know? Put in the calculator. So, oh man, we got to get moving here. 2x to the third plus 15. Nope. Oh. 2x to the third plus 15. I can't even type on this dang thing. There we go, plus 15 x squared minus 23 x. Oh, we're missing a 0 somewhere. There should be 3x intercepts. I gotta zoom out a little bit here. Alright, I zoomed out. I'm going to make a new zoom box here to see all of the zeros. That ought to do. Okay.
So this is negative 1, 2, 3, 4, 5, 6, 7, 8. That looks like it's pretty close to negative 9. Is there anything on our list even remotely close to negative 9? I'm talking about this zero way over here to the left. Do we need to bother with this one then? Probably not. Okay. This one here is pretty close to the y-axis. Does it look like it's right in the middle between negative 1 and 0? Does it look like it's right in the middle? Because the only thing it could be even close to is negative 1/2. Does that look like it's negative 1/2? It looks like it could be potentially. You can type in negative 1/2. So if you hit trace, you type in negative 1/2 or negative 0.5 and hit enter. Is negative 0.5 actually a 0? No. So this one here to the left didn't work. This one doesn't work. This is our only other shot What does that look like? Is it 1/2 or 1 1/2?
1.5.
Looks like it's 1 1/2, right?
Yeah.
Which fraction is that on here? 1 1/2. Looks like it's 3/2.
It is.
So I'm going to hit trace, type in 1.5. Is it 1.5? Yeah. So we know that 3/2 is a 0.
So we know that x equals 3/2 is a 0. Here's a slight problem. Just the positive, because it was positive 1.5. It wasn't the negative 1.5. Here's the problem, you guys. How did we show now for sure that this was a 0? Yeah, that doesn't work too well with fractions. That doesn't work too well with fractions. Let's do a quick little thing here.
I'm going to do this.
Well, I was going to do it on the board, but then they wouldn't be able to see it on here. So
I'll do it on here. Blank screen. If the 0 is x equals 5, what's the factor that it came from? X minus. This was on your test, by the way. You should have. If the 0 is x, or if the 0 is x equals -1, what's the factor that came from? You guys see most of this, right? The point I'm getting at is what happens when you have a fraction. What if the 0 is x equals 3/2? What crap kind of factor would that have come from? And I'm just to save time, I wish we had more time. Here's the factor. Tell me what the connection is. If this equals 0, wouldn't you add 3 and then divide by 2 to get positive 3/2? You guys see the connection here? What I'm getting at is we can't use synthetic division. If we can't use synthetic division, what other kind of division is there? Check it out. You're going to have to do this on your homework, but we can use long division. 2x minus 3 is the factor. And look at what we get. Remainders of? The remainder is 0. What does that prove? If the remainder is 0, what does it prove? That it is a 0. So for these funky zeros like this, x equals 3/2, you've got to figure out what the factor is here. In this case, it's 2x minus 3, and divide using long division. Got it? So anyway, this is halfway point of the lesson. You guys are going to be able to do the front page. So you're only doing 1 through 8 at this point. We don't have time to get to the back side. I want you to do the practice. It is good practice.